Hey everyone, welcome to Science in Perspective. So Google made an announcement recently that they have achieved quantum supremacy, that they can do something with their new Willow chip, which is based in quantum computing, and then it can run or solve a problem faster than what you would get with classical computing, which is of course the computing that we use every day currently. So classical computing, rules-based algorithmic computing is what runs your iPhone, your desktop applications, everything that we've been doing with computing. Quantum computing takes advantage of things like entanglement and superposition properties, phenomena that are inherent to quantum mechanics, and is able to run calculations faster. At least that's the idea. Now remember, Google made announcements similar to this in 2019 with their Sycamore approach, their chip, which was apparently going to do a problem a lot faster than classical computing, but then some researchers came out like 6 months or a year later and did not only matched what the quantum computer was doing, but did it even faster. So go check out my first episode in Science in Perspective, where I talk about that 2019 announcement and kind of relate it to the hype. But it also gives a really good background to quantum computing in general, if you're not too aware of how that works. Anyways, here we are in 2025. They've got this Willow chip. They make this announcement again. This is a different problem. And presumably they verified it a lot more than the 2019 because they wouldn't want to make the same mistake again. And so this Willow chip is able to take a problem that we'll look at in this episode, and I'll explain how they do it. And they're able to run a calculation that they think is about, let's say, 13,000 times faster than anything a classical algorithm or computer could do. Again, classical being the stuff that we're used to, right? The regular computation as is. Okay. So let's take a look at this kind of Willow chip, the science behind it. Let's talk about some of the quantum computing, the experiments, the problem that they look to solve, and then how they're relating that to classical computing. And I'm going to, after doing all that, kind of focus that into my main argument in this episode, that I don't think quantum computing should be used for what they're doing here. I'm not here to say it's not, the current announcement definitely has its skeptics, right? But I'm not here to say, is that really quantum computing? Is it not? Is it really better than classical? Is that... Sure, we can just, give them the benefit of the doubt and say, yeah, maybe they really have done what they say they've done, and it really is better for that problem in classical computing. But I don't think that's what we should actually be doing with quantum computing. I think there's a better thing to do related to complexity and emergence and a lot of the things that I tend to promote in science and talk about. But I'll get to that in a bit. Let's just kind of break down what it is Google has done, the problem they focused on. Okay, so first, let's just talk about why you should even bother caring about this, right? Like, isn't this still just computing, and isn't it just faster? Well, quantum computing, yeah, if it works, and maybe it already is to some extent, would be a lot faster than classical computations if you're comparing the same type of problem. So why would you care about that? Well, let's think of some of the things that are already taking advantage of computation today. Well, that's going to be most of anything, because software is essentially eating the world. So computation is playing some role in just about any aspect of life, any aspect of our economy. But let's use some specific examples. Let's say something like RSA encryption, right? So a lot of the security that you're using with your iPhone, with products that you use, applications, right? Putting in your password and all that. It's based off basically a factorization problem. They take a really big number, and then the problem is you have to factor the two numbers that had to be multiplied together to make that big number. And that turns out to be a pretty challenging problem. If you do that with regular computing, it can take you a very long time to try to solve it, if you can at all. It might even take you the age of the universe of regular computation to try to solve that problem. So trying to solve the factors that went into a really big number is a really, really hard problem. Categorically hard, you might say. But the idea is that quantum computing, if it could tackle that, if it was real, it would be able to approach that problem and solve it much more quickly, maybe in a few hours or maybe a few days. Now that would definitely change things. Hackers could use that to try to access things that otherwise would have been secure under the classical computing paradigm. And maybe on the bright side of things, people in quantum computing might be able to come up with better encryption protocols based on quantum computing to make things even more secure. So it's would be a real economic impact if you could speed up the calculation with quantum computing for things that we calculate classically currently, like encryption. What's another example? If you think about molecular structure prediction, that's a really big one, right? Pharmaceutical companies are constantly calculating the structure, trying to predict the structure of different molecules, because that would go into the drugs, right? So drug design. Materials science does this as well to some extent, right? They try to predict what different chemical molecular structures are going to be, because you have this strong connection between the structure of a molecule and the properties and the materials that end up getting created, or the drugs or whatever, the medicines that get created. So there's that kind of structure-property relationship. So that is an example of a calculation which currently classically takes a very long time. You can use the fastest supercomputers in the world, which are still classical, and you can try to model, let's say, predict the structure of a very small molecule, and it could still take you weeks of calculation, maybe even months, depending on how advanced the calculation is. So these are things that take a long time. Another one might be portfolio optimization, maybe in finance, right? These calculations that try to balance a lot of different things in finance, investment, stock options, market trends, and those can become very, very complicated calculations to run. So classically, those can take a long time. Maybe that would change things if you could get a quantum computer in there, get way more predictive, so the story goes, about the market, maybe how to best balance or optimize a portfolio, or things like supply chain logistics, right? Think about how much goes into something like, semiconductor industry in Taiwan, for example, and that just absolutely complex supply chain that makes that a reality. Imagine trying to optimize that or model that, and so forth, right? So there's all kinds of real calculations, obviously, that are going on today, and if those could be sped up 1,000-fold, 1,000,000-fold, 1,000,000,000-fold, whatever it is, thanks to quantum computing, it would arguably change a lot of things in today's economy and our life in general. Okay, now let's get into kind of more of the Willow chip stuff that Google's talking about and the problem that they applied the Willow chip to presumably demonstrate that it is actually doing something better than classical computing. So I want to make sure we understand that as a foundation. What are those core structures and laws, those kind of rules that we're operating within before we get into the Willow chip specifics? Okay, so a good way I think to do this is to look at nuclear magnetic resonance spectroscopy, NMR. This is the basic technology behind MRI, magnetic resonance imaging. So if you've ever had maybe a broken bone or something more serious, you may have gone in for some MRI imaging, and that technology is able to get some very detailed visualizations of what's going on inside the body, right? So MRI is based on NMR, nuclear magnetic resonance, and this is often used in chemistry departments and universities around the world. And it basically helps you identify or determine the structure of molecules, okay? So there's a number of different ways you might try to do that, but in NMR, you're basically putting your compound, right? So this could be like a solution of, let's say, toluene, which is the one they reference in this paper, actually, in the Google, because they basically say the type of problem they're solving is similar to what goes on in NMR. So maybe you take that molecule or a bit of a solution of it and you place it in a very large magnetic field, and that magnetic field essentially forces all the nuclei to align in one direction. Now, it might kind of sound weird to say, why would nuclei align in a direction, right? Aren't they just kind of spheres as an analogy? Well, they have dipoles, or at least certain atoms do. This could be like protons, which is the most common, right? You take the hydrogen proton, they act as little magnets. They kind of got a bit of a positive and a bit of a negative. And if you put them in a really strong magnetic field, like let's say millions of times what you would get on planet Earth, using, right, let's say superconductors, which was what they would do in NMR, you put them in a strong magnetic field, they all align in one direction. Okay, now that's kind of your starting point. Now, what they do is they'll align them in the direction, and then they'll take another pulse, usually an RF pulse, radio frequency, and they'll knock those nuclei dipoles into another direction. Let's say like 90 degrees from the magnetic field. Doesn't really matter, but let's just say 90 degrees from the magnetic field, okay? And then what they will do is those nuclei dipoles start to kind of relax back to their position. So you put them in the magnetic field, you get them all aligned in one direction, then you knock them another one, and then you kind of watch them relax. And as they relax, the different nuclei are relaxing depending on the environment that they're in. So this one might relax a little bit different than this one and this one. And the way that they're relaxing is telling you something about the actual structure, because as the nuclei, which is the center of the atoms of that molecule, are relaxing a little bit differently, they will, if you can get the signal from how they're relaxing, it will elucidate something about the structure. Now, of course, it's a little bit more involved in that. There's different types of relaxation. And typically what they do is they do the first RF pulse, and then they'll do another RF pulse to create what's called an echo, which is essentially kind of a mirror of what that original signal looked like. I don't think we need to get into too much details about how this works, but let's just explore this a little bit more, because Willow does call what they do an echo algorithm or an echo approach, and so I want to make sure it's clear why they're calling that an echo, right? Okay, so we had all those nuclei in the different molecules of, let's say, toluene or whatever it is we're looking at. We put them in a strong magnetic field, they all align, we kick them 90 degrees, let's say, and it's not really a direction, it's more of a phase, but I don't think we need to worry about that. So the phase kind of goes let's say 90 degrees, the RF pulse goes, they put them all into phase. It's as if they're pointing the same direction. And then they start to precess, which is they kind of move like a top would, right? Because you've got the magnetic field fighting, you got kind of like two things pulling in different directions, just the way you have angular momentum kind of fighting gravity with a top and it causes it to precess. That precession basically enacts Faraday's law, which puts a voltage in the RF coil. So as those things are in phase and then starting to dephase, because they start to do different things. It's like if I put a bunch of people on a dance floor and at first they're all moving exactly the same, and then a few seconds go by and they all start kind of moving a little bit differently. That's kind of like dephasing. They're going out of phase, right? As they go out of phase, the original in-phase signal that was causing the high voltage is now starting to drop. So if you look at the signal in nuclear magnetic resonance, you'll see it go up at first, and then it will kind of decay down. So they start in phase, which we in how the different RF pulses are working and how phasing and dephasing works. But it's a pretty basic idea, even though it sounds a bit complicated, because as you put them all into phase, it creates a voltage, you kind of get a current, and you'll actually see the signal come. And as they start to relax, the signal changes. So you're looking at how that signal changes to elucidate the molecular structure. Okay. Now, as a problem, because we're talking about the type of problem that the Willow chip, which we'll get to in a bit, tries to solve, it's similar to this. I want to use an analogy here because I don't want to get caught up in too much jargon with RF pulses and magnetic. I don't want to get confused by that if you're not used to NMR. So let's just think of a Rubik's Cube, okay, as a kind of a high-level analogy. Imagine you have, I give you a Rubik's Cube, but you've never seen what a Rubik's Cube is before, okay? And you don't even know what the end state is supposed to be. I don't really tell you much about the objective. You just know that there is some final state. So I give it to you all jumbled up, and you have to try to figure out what the final state is. It's kind of like trying to predict or determine what the final molecular structure is, right? It's an unknown substance. You don't know what the structure is. Nobody's there to tell you, what the end goal is other than just finding the structure. So it's like I give you a scrambled Rubik's Cube, and you've got to figure out how to get to the end state. Now, if I never told you what the end state was, how would you know? Well, you might try to kind of figure out the dynamics of the rules of the Rubik's Cube, the way it evolves. Like you start spinning it, you'd notice I can start to make certain colors match together, but if I change something over here, it kind of ruins the colors over here. Maybe I've given you some hints at the objective, like colors are kind of supposed to be clustered together, right? But you try to figure out the dynamics and eventually try to get what maybe a final state would look like. And again, maybe I do tell you what that it's supposed to be all the same color on the side, or maybe I give you some hints to it. But the point is, in order for you to get there, you've got to kind of figure out the dynamics of how the thing turns, what the constraints are, what does and doesn't do, right? If you could figure out those dynamics, you might be able to kind of replay your steps to try to get it to go to some kind of final state. It's not the best analogy, but the point is you're trying to take something that's scrambled and decode it into a more unscrambled state. You're trying to figure out what that unscrambled state looks like. That's kind of what NMR is doing, right? It's in that case, you purposely scramble the molecule, and then as things start to relax and go back to their original positions, you're trying to figure out what those scrambling dynamics actually are and look like and why the different atoms are different, so you can elucidate the positions and the environment that they're in and eventually get the structure, okay? So hopefully the Rubik's Cube analogy kind of makes sense. Now, I'll use some other examples to make this a little bit more clear. You might have something like cryo-electron microscopy, where you're actually trying to take quote-unquote images of molecules themselves, right? Now, this wouldn't be like using a camera with photons of light because the wavelength is too large, and we're talking about atoms and molecules. You need a much smaller wavelength. So electrons are much better for this. They have a lot tighter, smaller wavelengths. So electron microscopy takes advantage of the extremely small wavelength of electrons to try to resolve images of things that are very small. You see this in scanning electron microscopy. You see this in transmission electron microscopy. all kinds of different versions. But cryo would be used for something like soft molecules. You might be trying to look at bacteria or viruses or proteins or things like this, like molecules or assemblages of big soft molecules that tend to degrade. That's why cryo, you keep it cold. Anyways, what you get is a bunch of kind of two-dimensional slices of the molecule, let's say. And because they're two-dimensional, you don't really know what the molecule looks like, but you're just kind of getting hints at it. And you need to now piece all those together and try to kind of reconstitute or elucidate what that ultimate final structure is. Same type of idea. You're getting something scrambled, and you're trying to use a bunch of different pieces and knowledge and information and data and dynamic information to get at the true source structure that is, in this case, the molecule, right? Another example might be something like DNA sequencing, right? If you go to sequence the whole DNA, you're not going to get that in one snapshot, right? You might get pieces of the genome, pieces of the DNA. You've got to bring those together and then try to figure out, based on rules and laws and how things work in the chemistry, what that actual full sequence is going to be. Or X-ray diffraction in material science. You take crystalline material. They do this stuff in material science all the time. They bombard it with X-rays. Those photons kind of scatter all over the place. You're getting kind of that scattered images, and you take all those different images, and then you have to try to figure out, based on the way scattering happens and the way, maybe the weight of the nuclei and all this, what the actual crystalline structure looks like. Okay, so it's the same idea. It's like I give you that scrambled Rubik's Cube, and you got to figure out how to get back to its original state, which I guess would be like the solved state. And you don't really know what that solved state looks like, though. So all you have are the kind of the dynamics and the rules and the different information to try to almost reverse the process back to that original structure. I hope that makes sense. Okay, so now let's get to the Willow chip that Google's doing. That's the kind of problem they're taking, because it turns out that's extremely computationally difficult to do. Okay, if you want to predict the structure of a molecule, right, I used that example at the beginning, right, in drug design, for example, right, or material science, it can take weeks and weeks and weeks to run a calculation, even on just one small molecule, let's say the structure on a supercomputer, right? It's a very challenging thing to do, to take something scrambled and to get it back to its original state. And that's because the scrambling is chaotic. It's super dynamic. You're dealing with high levels of interactions between all the pieces. So it's not an obvious thing, right? You don't have like nice analytical mathematical solutions to this stuff. You have to use approximation methods. You have to iterate millions and millions of times over things to try to figure out what that final structure is. So that's the kind of problem that Willow attacks. Okay, so what is Google doing with their new approach? So they take their Willow chip, which is basically 105 qubits. Okay, now again, go back to the first episode. You don't know anything about quantum computing, but they use qubits, and they can get those qubits to do their logical operations by using quantum gates. And this is usually done, it could be like with lasers or some type of EM radiation that they're trying, microwave or whatever, that they try to change the state of a quantum something. It could be a small piece of, material that's maybe superconducting, and it's held at a really low temperature. Again, it doesn't really matter. It's a quantum object, if you will, that has quantum properties, right? It's very small. It's very cool down to low temperatures, and they can use these gates to change the state. They might be changing the spin or something like that. So they have 105 of these qubits, and these qubits do what they do, which they can do entanglement, they can do superposition. You can kind of control, to some extent, how the entanglement and superposition happens based on those quantum gates that do the logical operations. Okay, so what do they do? So what they do is they basically run the process forward, whatever their algorithm it is. In some sense, it might not even matter what this is. It's just some process they've defined, right? And they run it forward through the 105 qubits, and then they run it in reverse. But what they do is, before they run it in reverse, they add a perturbation. So they change it. It's almost like if you were to damage one of the qubits or something before you run it in reverse. Okay? So it's kind of like you take your Rubik's Cube. I go to scramble it. Okay? And but before I give it to you, maybe I was going to, I'm trying to think of a good analogy. Maybe I kind of like half scramble a cube, which isn't that hard for you. But then I make a few more twists in the half scrambled cube, and then you have to reverse it from that additionally scrambled state. So it's kind of like the dynamics that you have to figure out are a little bit harder. Okay? Or maybe the better analogy is, I could give you almost a completely solved cube, but I perturb it a little bit more. So there's more for you to try to reverse, if that makes sense. Okay? Because of that perturbation. So what they're doing is they're trying to create a problem in a quantum computing setup that is similar to all those examples I gave over at the end. I gave when I was talking about nuclear magnetic resonance, NMR. Okay, whether that was like DNA genome sequencing, whether that was molecular structure prediction, right? The X-ray diffraction and all that kind of stuff. The cryo electron microscopy. Same idea, or just NMR itself, right? Where you have this kind of scrambled state and you're trying to reconstitute it back to the original structure. They set that problem up with quantum computing. The way they do it is, again, they have a bunch of qubits, 105. They run a process forward, they perturb one qubit, and then they run it back. So they've kind of scrambled the Rubik's Cube a little bit so that when they go to run it back, it's now kind of messed up. And what they want to do is see if they can recover the original signal, despite it being messed up. Okay, so presumably they already know what the original signal looks like because they know they deterministically ran something forward, but then they perturb it, and that perturbation kind of chaotically, almost like the butterfly effect, chaotically kind of messes up and dissipates and gets chaotic the way a chaotic system would, so that then when you go to look at it, you're looking at a messed up version. You're looking at kind of like a scrambled Rubik's Cube. Okay, so if you can recover the Rubik's Cube, if you can get back to the original state, then it means you've solved a categorically hard problem to solve, right? We talked about supercomputers being used to try to understand molecular structure. It's the same idea, right? They perturb that qubit, but they can still get back the original signal, okay? And they call it echo because it's similar to the echo signal in NMR, where they do, kind of the second RF pulse. It scrambles things, and then they look at the dynamics as it starts to go kind of from out of phase and back into phase, or from in phase to out of phase, right? It's the same idea. It's like an echo signal that they need to now kind of put back to the original. Maybe a better analogy to understand that would be like sonar. If you think about aiming let's say you like echolocation in a bat, right? You're going to put out a bit of sound, and then that's going to come back to you. But you have to infer the location of where that sound came from. You have to pinpoint that somehow. Again, it's kind of like trying to take all this random chaos, this chaos that's coming at you, and kind of reconstitute it back, right? Reverse the process back to where it came from. It's that idea. So the qubits, run it forward, perturb it, run it back. When they run it back, it's messed up. Can you reconstitute it back to its original pinpoint location, or however you want to think about that? Can you reclaim the original signal? Okay. So they call this essentially the echo algorithm. It's on the Willow chip, and this is their setup. And they say that they did it, and they can, and it's an example because that's a hard problem to try to get the signal back, right? Something like classical computing would maybe take thousands of years to compute. They can actually do this in however much time it was. Not thousands of years, right? A very fast calculation, and it was done in a quantum computing setup. Okay. So that's what they did, and that's the announcement. Obviously, that's high level, and you can go check out the paper yourself if you want to kind of get more details on that. But I think that Rubik's Cube analogy and kind of the echolocation is kind of a good example. And we have similar technologies to this. So I mentioned sonar, which is normally not going to do a lot of that kind of reconstitute the signal. It would just kind of like, let's say, you do the sound, it bounces back, and you kind of analyze how it's bounced back, and you kind of know a rough location. But if you wanted a really advanced version of sonar, you might do something like that. In fact, there's something called TRA, time reversal acoustics, which does do something like this, and is implemented in certain technologies. There are certain types of, let's say, high-performing ultrasounds, which might try to do kind of non-invasive, let's say, a tumor targeting within the brain of a human being by using this type of time reversal acoustics. It's kind of like sonar, but you're trying to pinpoint exactly where the signal came from, right? If you hit something with sound and it bounces off tissues, it's going all over the place chaotically, right? Just like the perturbed qubit. It's going chaotically, and now I've got to run it in reverse and piece it back together to where it actually came from. So it's a type of focusing. And there's a few other examples of time reversal acoustics. That same idea, right? Whether that's advanced ultrasound, or they might be doing some advanced sonar with that type of thing. But yeah, I think that's a good analogy for what that would look like. Okay, so let's just do kind of a really quick recap. I said at the beginning, look, if quantum computing is real and it can really make calculations a lot faster, presumably that would have a big impact on our economy, on our world, because so much of our world is running on classical algorithms right now, right? Software is just about everything. So if you can make the calculations go faster, it should make a difference. And it makes sense, because if you look at things like encryption, if you take a look at things like molecular structure prediction, if you look at portfolio optimization in finance, or you know, the different, you know, I'll use Taiwan as an example, supply chain logistics, sorry, and you try to maybe optimize something there. These are all running on calculations that take a ton of time, right? And we took a look at the problem that Willow ends up kind of using as an analogy to showcase their supposed quantum supremacy. We took a look at nuclear magnetic resonance, right? You put all those molecules in a magnetic field, you kind of knock them out, you watch them kind of relax back, and then you try to unscramble that information back to the original structure, right? I said that you can see that in things like cryo-electron microscopy, you can see that in like DNA sequencing, X-ray diffraction, all kinds of examples, right? Even particle accelerators, right? Like a large hadron collider might collide two particles together, and you get this mess of stuff coming out of the collision, and then you kind of reverse the process almost back to what was there originally, kind of, right? It's that kind of stuff. It's super common in science. Then I said, okay, the Willow chip is basically doing that problem with qubits, right? Got 105 qubits. They run that process forward. They perturb something so that when they run it back, it's messed up, and then they got to reverse it back from that messed up state back to the original state. And if they can do that, because they have the thing to compare it to, they can validate it, they can verify it, then it means they've solved a genuinely hard problem. And if they can do that quickly, then presumably that's a lot faster than classical computing. Okay, I hope that made sense. So that's basically the Google announcement. That's the problem space that they're operating in. Now, what is kind of the core, I think, most important invariant pattern here? Like, what is the more profound kind of thing happening? Well, here's my issue. I'm not saying what Google proclaims to have done is not necessarily true. It probably is. I mean, I think there's probably reason to be skeptical as well. But yeah, sure. I mean, I think they presumably at this point know how to set up a quantum computing experiment. They can use their quantum gates to run processes forward and backward. I would imagine they could perturb a qubit. And if they said they were able to reconstitute one of the original signals so they could unscramble something and they could do it faster than classical computing could, I mean, as long as they did their work to verify that the way that you're supposed to within the quantum computing paradigm, then yeah, maybe they did do that. Okay, so that's fine. My issue is I'm not convinced that this is what quantum computing should actually be doing. Now, what do I mean by that? Well, quantum systems, quantum mechanics, are able to achieve a genuine level of complexity. Okay. Complexity being many, many pieces with lots of interactions. Now, that's not the same thing as chaos, and it's definitely not the same thing as determinism. So when they set up their experiment with the Willow chip, they use a deterministic algorithm, right? They run it forward, perturb it, run it back, and then deterministically try to figure out the original signal. Now, understandably, they're comparing it to deterministic computing, which is the classical computing that we use today. It's all deterministic, it's rules-based, right? Not counting AI, but basically, even the scaffolding of AI is still all rules-based, Turing machine type usual computation, right? So it's by and large a deterministic thing, and that's what they want to compare their quantum computing to. So that's why they do that. They do a deterministic thing and show that even though they're doing it deterministically, they can do something a lot faster. So I understand why they do that, but I don't think that's a good comparison to make. I don't think that's what quantum computing should be used for. I think that's kind of like putting a Ferrari in a dog race, right? Because what chaos is not is complex. Okay, chaos and complexity are not the same thing. In fact, they're quite different. Because chaos, by definition, is still deterministic. So when they perturb the qubit and it trickles out and goes all over the place, if that truly is a chaotic system, the reason they can reverse it is because it's deterministic. Deterministic things can be reversed. Non-deterministic things, by definition, cannot be reversed, right? Not anywhere near as precise as that. And I would say when it comes to genuinely natural complexity, not at all, right? You can't unscramble the egg, right? Nature does not have reversible processes like that because it's not based off of simplistic deterministic causal chains. It doesn't have chains of causality that lead to the thing that we observe. Okay, and I argue for this a lot. And so what I think quantum computing should be used for is to create systems of genuine complexity. Use the entanglement and the superposition to not create chaotic deterministic systems, which are still pretty simple, but to create genuine complex systems that cannot be reversed and use that to do the computation. Now, what does that mean? Well, what it really means is emergence. Chaos has nothing in common with emergence, but complexity is all about emergence. It's the hallmark property of complexity is emergence. And emergence, by definition, is not causally connected down to the root cause of things. It does not have properties that you find in the small pieces, right? Complexity is not more, it's different, okay? So if you use quantum mechanics to create genuine physical complexity, and then you get emergence out of that, the emergent properties could be used to actually solve problems. And this is, of course, what we see in nature. Now, before I get into the nature stuff, I mean, this is essentially what you're seeing in AI with deep learning and large language models today. Okay, you've got, again, rules-based coding for the scaffolding, but you're iterating millions and millions and millions of times, and what you're getting is emergent things. We know they're emergent because there's no way to peel back the layers and reverse engineer. It's never going to happen. AI is a black box, not because it's difficult, but because there's nothing in the black box in the causal sense. There's no causal chain of reasoning that you can go from the input to the output because it's not based on causality like that. It is emerging. A new pattern forms. A new pattern forms at a higher level of abstraction that does not exist at the lower level. So it's not about chains of causality. It's not about deterministic algorithms leading to the output, right? This is why AI is not programmed. This is why no scientist or engineer in deep learning knows exactly how it works. In fact, not even close to how it works. They know how to set it up, but they don't know how the outputs are produced. Because know usually means determinism. When you say you know something, you're able to draw how this hits this, hits this, hits this until you get to the output. That's not what happens in deep learning, right? So deep learning is our closest example of what I like to call engineering emergence. Or, I wrote this in my book. I have a section in my book called, we need to engineer emergence. Okay. And I'll get to there's a paper out actually called Engineering Emergence, which I'll get to in a second. But I don't think it takes the right approach, but I'm happy that in spirit it's starting to go in this direction. But I want to make one distinction clear here. So when I say, deep learning is achieving emergence in kind of a roundabout way, right? Because we still set everything up in a rules-based fashion with classical computing, and then we allow it to just kind of run off and go on its own, and then informationally you get things emerging, information that did not exist in the real data, okay? In the original data, right? It's a new synthesis, it's new things that are coming, it is genuinely creative, despite what some people might not like, right? It is a type of emergence, for sure. But it's not physical emergence, right? It's not like you actually have a physical system that has achieved a genuine complexity. It's like an informational complexity. But I kind of think of quantum computing as the ability to create almost a genuine physical emergence, like the way matter is in nature, right? Because it is nature in a lot of ways. It's kind of a contrived version because you're using isolated qubits and then getting them to do what they do in a very controlled fashion, right? But it is a genuine quantum system, like a molecule, like a bunch of molecules, like a genuine complexity that we see in nature. That's what you should let quantum mechanics do. You should let it be nature, right? Let it achieve genuine levels of complexity. And then in that case, you wouldn't be getting deterministic algorithms going backward and forth because it wouldn't be deterministic by definition. Okay, so what is it? So I'm arguing for engineering a type of emergence. Let quantum computing actually be quantum. I don't think you're really letting it be quantum. I understand you got quantum gates and qubits, but when you're setting it up in this very strict deterministic way, and I know why they're doing that because they're comparing it to classical computing, but you shouldn't be comparing it to classical computing. It should be nothing like classical computing. Again, it's like putting a Ferrari in a dog race. It doesn't make any sense. You should be complex because that's what quantum mechanics is able to achieve, obviously, because it's in nature. Nature doesn't have deterministic algorithms. It doesn't have anything even analogous to a deterministic algorithm working the way it does. Anytime you see someone try to frame it like that, that's an absolute, it's a falsity. It's a fallacy, really. Okay, it doesn't make sense. That's not what emergence is. It does not have the determinism. So let quantum mechanics become genuinely complex, not chaos, not little deterministic perturbations, actual complex, right? Which means the outputs it produces cannot be traced back, cannot be reversed by definition, and those outputs could be used to solve problems, right? Now, does this happen anywhere in nature? Well, sure, right? I mean, actually, I would argue, as I do in my book and other places, that this is actually all of nature, right? This is really how nature, quote unquote, solves problems. When I say nature solves problems, I don't mean it's got some purpose. I mean that you can view it through the computational lens. And I think it really makes sense to do that, okay? If you have a tornado that's forming and it's got its vortex, well, that's a solution to a problem because it's finding, you've got hot bodies of air, you got cold bodies of air, and it's in a state that's kind of out of equilibrium and needs to kind of solve the problem of balancing, let's say, air pressures. Well, of course, that's what a tornado is, right? It's solving a problem of trying to balance a complex situation where you've got all these different air pressures and it needs to find a lower pressure state is one way to look at it, okay? If you just think about the coupling between electrons or nuclei in molecules, right? They reach new energetic states which is a type of solving a problem, right? And I'll give you an example of a bit more specific on that this is actually emergence that's doing it. Okay, but you can use, the Starling murmurations, you can use the shimmering of bees, you can use what termites do. It doesn't matter. You can use those kind of more classical examples of emergence. Everywhere in nature, you're seeing emergent solve the problem, not some deterministic algorithm that runs step by step to solve a problem. That doesn't exist anywhere in nature. That's not how nature solves. Nature solves, it computes its problems via emergence. And that's why and I'll give you some more examples in a second. I'll give you a core example in a second, just to dig into that before I kind of sign off on this episode. But I wrote in my book that we need to engineer emergence. And this is kind of what makes me think of it. I look at what Willow's doing, making these comparisons to classical computing, and I'm like, well, that's not what quantum computing should be doing. It should be becoming complexity, establishing genuine emergence, which is not reversible, and using the emergent outputs to solve problems the way nature does. There is a paper that came out pretty recently by Abel Jansma and Eric Hole, and it's called Engineering Emergence. So I saw that title and I got quite excited because I had written in my book that literally using that same type of terminology, we need to engineer emergence. Now, this seems to be more of a causal picture. I think their approach is too causal. It seems to be in spirit to kind of renormalization, where you're trying to take fine grain and coarse grain, and they try to. It's interesting, and it's definitely worth a read. And I'm not trying to disparage the paper at all, but it's not the approach that I think is correct, and it seems too causal. It seems like the usual physicist's approach. Physicists don't like to let go of their reductionism, so they try to take a very kind of upward causation approach to emergence, which is kind of like saying you basically think emergence can be causally reverse engineered or traced back to the origin point, right? The way that they're kind of doing with the perturbation and the chaos, right? Which is, I don't think, quite correct, okay? In fact, I don't think it's correct at all. I don't think emergence has upward causation. I don't think that's what it is. I think each level that you look at in scale is a completely different manifestation altogether. It's got its own causal structure. It does not come from the layer below. Pieces have to come together, but once the emergent pattern arises, it's a completely different thing. So I like in spirit that there are papers coming out now called Engineering Emergence, because at least in spirit, it's got the right idea. I think they kind of get that, hey, maybe emergence is going to solve the truly hard computational problems. I don't think it's an upward causation thing. I don't think you can use kind of these older physicists' approach of renormalization and stuff. I don't think nature uses averages, and I won't get into the details, right? I think it's true emergence. It's not more, it's not causally connected to the layers below it. It's a completely different thing. In any case, you should be using the emergent outputs to solve the problem. Okay, so before I end the episode, let me just give you an example. There's this paper that came out recently. I mean, you could use anything, but here's an example. Came out in Nature, I believe, and it's called Vibronic Coupling-Driven Symmetry Breaking and Solvation in the Photoexcited Dynamics of Quadrupolar Dyes. And this is by Antonietta DeCio and Christophe Leonau. Hopefully I pronounced it okay. Don't need to go into a ton of details, but here's an example where, so they'll take a molecule and they'll basically photoexcite the molecule and they'll put it into this kind of symmetric state, okay? Meaning the electrons are kind of the same on both sides is a simple way to put it, right? It's all kind of just symmetric. And then they'll measure, and they'll do this with lasers at the femtosecond scale, right? So with femtosecond laser pulses, they'll notice kind of how things are changing in the molecule over time. Like by time, I mean femtoseconds, right? So very, very short periods of time. And what will happen is all of a sudden you'll get the spontaneous symmetry breaking. And so the electron, you kind of think of it as electrons kind of shifting to one side. They all of a sudden pick one side over the other. There's like a bias there. And spontaneous symmetry breaking is kind of one of these standard telltale signs or hallmarks of emergence. Not always, but quite often, right? And so you could see this as emergence happening at a very small scale. And again, I was using the tornado example. I talked about electron-electron coupling. What's happening here is you are actually getting coupling not only between the electrons, but also between the nuclei and between the electrons and the nuclei. Okay, and that's why it's called vibronic. It's like mixing electronic and vibration together, right? So you get vibronic coupling. So there's this very genuinely complex system that is establishing its own pattern via symmetry breaking. Everything kind of shifts to one side. It's a new pattern. The pattern was not put there by anything else. It just self-organized into that. And so it is a type of emergence. And that emergence is obviously solving a problem. There'd be all kinds of examples what this might be. It might be something related to solvation. It might be something related, like chlorophyll, for example, if we're not what they're doing, but let's just say, the photo excitation that happens in photosynthesis, right? And you get this kind of separation of charges in a way, and it kind of leads to energy molecules and all that kind of stuff. You get similar things where in the photoexcited state you get a symmetry breaking. That's a generally emergent pattern, and obviously that is solving a problem if you look at it through the computational lens for plants, right? And you could use hundreds and thousands, well, you could use infinite, near infinite examples, because this is what nature does. I'm just trying to give you another example of it is emergent pattern formation that doesn't come from underlying levels of causality that solve the problems that make nature tick. Okay? So when you go to something like what Willow's doing, maybe that's totally true. I'm not necessarily even skeptical about what they accomplished. Maybe they really did. That's cool. You're making classical stuff. You're making comparisons to classical computation and showing that that can go quicker. But I don't think quantum computing should be doing classical things. Why are they showing deterministic algorithms? I know for the comparison, but quantum mechanics, if it really is at the heart of nature, can obviously bring about a level of genuine complexity. Complexity is not chaos. It's not deterministic. Complexity leads to genuine emergence. Emergence is what we need to engineer. Emergent outcomes in nature. And I think that's the way we should be using quantum computing to solve problems as well. Okay, that's it for this episode. I hope that made sense. Hit me up on either Twitter, now X, or if you're on the Science in Perspective app, right? You can join the forum, become a member. You can talk. You can ask questions. There's lots. There's some bonus material on there to learn more about techniques and mindsets and related to science and transcripts and all that kind of stuff. So anyways, go ahead and check out scienceinperspective.com if you want to become a member. Anyways, thanks everyone for listening, and for those of you who have been watching. Until next time, take care.